Okay, so previously we have just seen another typical example, and one look. This is a course that most of the things we have to understand the fundamentals, right? And one or two things I leave it up to you when we'll solve some numericals. Why we have done so? So you will try to answer that yeah, and at the time if you can't, will respond to your forum, right? So as many as much as possible we have tried to incorporate varieties of problems and understand. We have to see that whether everything in understanding is clear or not. So for example, you take this example that your that switch in that your switch in the circuit in shown figure has been closed for a long time. Long time means that it was, it was closed, it was right, and that means it has reached to a steady state. Say at long time switch was closed, right, and finally what happened, if it is your you have to find out the initial condition for that, right, and it is open at t is equal to 0. You have to find out Vt for t greater than equal to 0. Also you calculate the initial energy stored in the capacitor. In this circuit that this switch was closed for long time. If the switch is closed for long time means this switch was closed for long time, right, and at t your what you call at t is equal to 0, the switch is just opened, otherwise it was closed. If switch was closed for long time, you know that for the DC supply the capacitor will behave like an open circuit, right. So it will act as open circuit. This two terminal will act as open circuit. So in that case what will happen, as this is open circuit means it is not there, and that means nothing is flowing in the 10 ohm resistance, and finally a current will flow through this only, right. So if you try to find out that what is the if capacitor acts as open circuit, that means this is the voltage V, say across the capacitor, this is 20 millifarad if it is open circuit. So in that case what will happen, that you find out this 30 ohm and this is your 50, it is just hold on, let me see, this is 90 ohm, right. So this is your I, this is 90 ohm. So what is the current then? I will be is equal to 20 divided by your 30 plus 90, right. So it is 20 volt. So 20 divided by your 120, that is 1 upon 6 ampere, that is the current your I. Then what is the voltage then? As this is your open circuit, so it is not there and no current is flowing through this. So this is the voltage that open circuit, your what you call that voltage across the capacitor when this was closed, right. This was because at t is equal to its switch was open at t is equal to 0, before that it was closed. So this current is I is flowing, right. So in that case what will happen, the voltage across this will be 90, because this no current is flowing here, it is open circuit, and 90 into your 1 by 6, that is your 15 volt, right. So yes, that means that your what you call when switch was closed for long time, right. So at that time voltage your what you call across this capacitor is just 15 volt. So everything is given there. Therefore if you look into the circuit when switch is closed, this is the equivalent circuit whatever I have done for you, right. So this is the initial condition, that's why writing Vc 0. So current through this I told you 20 upon this is this no current is flowing through 10 ohm resistance because it is open circuit. So I will be current flowing through this, I showed you that 1 upon 6 ampere, then Vc 0 will be 90 into 1 upon 6. So that's why it is 15 volt, that is the initial voltage is 15 volt. Now when t greater than 0, the switch is open and the equivalent RC circuit, now when t is equal to when switch is open, then this part is gone. When t greater than 0, so the switch t is equal to 0, the switch is open, that means this part is gone, right. So only this part is there. So let me clear it. So in this case this is the equivalent circuit, right. This is the, so 10 ohm and 90 ohm are in series and it is 20 millifarad, and initial capacitor was charged at Vc 0 is equal to 15 volt, that we have seen, right. So if then for t then your Req equivalent will be 10 plus 90, so 100 ohm, and time constant is C into Req, that is Req into C. So Req is equal to 100 ohm and C is equal to 20 millifarad. So 20 into 10 to the minus 3 farad. So it is second. So 2 second, tau is equal to 2 second. Thus the voltage across the capacitor for t greater than equal to 0, we know this, no, Vt is equal to V0 e to the power minus t by tau. So V0 is equal to Vc0 is equal to 15 volt, that we have got it, that, just hold on. So V0 is equal to Vc0 is equal to 15 volt, that this is the 15, and your tau is equal to 2 second. So it is t by minus t by tau, so e to the power minus 0.5 t, right. And omega c 0, that is initial energy stored in the capacitor, half C V0 square. So half C is 20 into 10 to the minus 3 farad and V0 square, so 15 square, it is 2.25 joule, right. So next is that source free RL circuit. We saw till now, we saw source free RC circuit. Now we will see source free RL circuit. So philosophy will remain same, just as it is inductor. So we just have to see how it happens. So this figure 12 shows the series connection of a resistor and an inductor. Basic objective is to obtain the circuit response, which will be natural response, because it is a source free circuit, which will assume to be the current IT through the inductor. So this is a simple circuit, this is inductor and this is resistor and this is the current I, right. And polarity is taken, current, here it is plus minus, here also it is plus minus. I mean current is moving like this current I, right. So that passive your, what you call this, your VRL, that whatever you have taken, that passive sign convention, right. So this is a source free RL circuit. Now if you apply in this loop the KVL, it will be VR plus VL is equal to 0. You apply KVL, so VR, so now you know everything, all these things have been discussed before. So VR plus VL is equal to 0, right. So let me clear it. So you assume that at time t is equal to 0, we assume that the inductor has an initial current I0, right. So capital I suffix 0, right. Or we can write small I, that 0 is equal to, that is at t is equal to 0, this is the current I all the time. Perhaps we are not writing IT, but this current, it is actually IT, right. So initial current, we will assume I0 is equal to that capital I suffix 0. So I0 capital I suffix 0, right. So this is the initial condition. We assume that inductor has an initial current like this. So let me clear it. So and the corresponding energy stored in the inductor, that is initially W0 is equal to half L capital I0 square. So this is equation, some equation numbers are given, understandable to you. So if we apply KVL around the loop, we will get, I told you, VL plus VR is equal to 0 in that circuit. Here VL plus VR is equal to 0. So but we know that VL is equal to L into di by dt and VR is equal to IR. So if you look into the circuit, here it will VL is equal to L into di by dt and here VR is equal to IR, right. So that means L into di by dt plus IR is equal to 0. That means di by dt plus R upon Li is equal to 0. So or di upon I is equal to minus R upon L dt, right. So integrate on both sides. So I actually varying from initial current I0, that is I0, to at some time t IT. So di upon I is equal to minus, it is 0 at t is equal to 0 to t is equal to t, right, R upon L dt. So this is at t is equal to 0, the initial current was I0, and here your what you call, here it is your this one, just there should not be any confusion. This one, this limit I have written capital I0, better it should be small I0, right. And small I0, and I told you small I0 is equal to capital I suffix 0, right. So it is small I0, that is better. So it is, and this side, right hand side, is minus 0 to t R upon L dt. Now you integrate, right. Let me clear it. So now if you integrate, it will be a natural log I t upon small I 0. Actually, this is small I 0, this is small I 0, and small I 0 is equal to I 0. So, it will be I t upon I 0 is equal to minus r upon L t. That means, I t is equal to I 0 into e to the power minus r t upon L. This is equation 23. This is chapter 6. So, this thing. Now, the 23 shows that natural response of the RL circuit is an exponential decay of the current, right. So, this is the your what you call the plot of your I t when t is equal to 0, when t is equal to 0. So, I t is equal to this initial value, that is I 0, and it is decaying, right, and it is written is equal to I 0 it was t minus tau, and tau is equal to L by R, right, that is your time constant of the circuit, right. So, for RL circuit, time constant is L by R, whereas for capacitor it is your R C, right. So, this is the plot. So, this is I explained, tau is equal to, therefore, I t is equal to I 0 e to the power minus t by tau. So, voltage across the resistor is V at t is equal to I into R. So, this is your I and this is R. So, substitute I here, it will be I 0 into R e to the power minus t upon tau. This is equation 25. Now, power dissipated in the resistor is that P t is equal to, at any time t, P t is equal to V at t into I t. So, this is your V at t, that is I 0 r e to the power minus t by tau. So, I 0 r e to the power minus t by tau, and I t is equal to I 0 e to the power minus t by tau. Therefore, P t is equal to I 0 square r e to the power minus 2 t upon tau. This is equation 26. Now, energy absorbed by the resistor is, right, the energy it is W at any time t, W at t is equal to 0, you just integrate 0 to t p into dt. So, 0 to t, and this is the expression for p, that is equation 26. You put it here I 0 square r into e to the power minus 2 t upon tau dt. You integrate and simplify. If you do so, you will get half omega t is equal to half L I 0 square into 1 minus e to the power minus 2 t upon tau. This is equation 27. So, at t tends to infinity, that is your omega r infinity is equal to half L I 0 square is equal to omega 0. Omega initially also stored, initial energy stored half L I 0 square. Again, the energy initially stored in the inductor is eventually dissipated in the resistor, right. So, this is, hope these things are understandable to you, quite simple, right. So, now next let us take one example. In this figure, you have to determine I t and I y t given that I 0 is equal to 1 ampere. So, this is the circuit, one D or what you call one dependent voltage source is there, right, 3 I plus minus terminal polarity has been marked. So, given that initial condition, this is I and this is I y, you have to find out I t and I y t given that I 0 is equal to 1 ampere. So, what you can do is you just if I make it like this before this thing. So, this is one loop, this is another loop you can take, right, and if this current is I 1, this current is I 2, right. So, you can make it that you have to apply KVL, and accordingly we have to solve it. So, let us see. So, in this case, this is that your call, this is what I have taken, right, and on the original circuit, in the previous circuit, it was given that this is my I and this is actually I y, this was given, right. So, basically the way we have taken the loop, it is I is equal to actually I 1 or I 1 is equal to I, and I y is current flowing through 2 ohm resistance, direction is this way. So, I y is equal to your, in this direction we are taking. So, it is equal to I 2 minus I 1, right, because this I 2 is going like this and I 1 is going like this. So, resultant will be I 2 minus I 1, and that means my I y is equal to basically I 2 minus I 1 is equal to I. So, it is I, right. So, that is all these things written, but just for the purpose of our understanding I am writing here, right. So, next that means if you look into this, you apply KVL here first, you apply that is whatever I have given, that I 1 is equal to I, and I1 is equal to I2 minus I1 is equal to I2 minus I. So, here you apply KVL in this loop, right. So, if you do so, then you will get 0.5, it is 0.5 Henry given. So, L into di1 of dt. So, it is 0.5 di1 upon dt. Then we are moving your clockwise. So, it will be 2 into plus 2 into I1 minus I2. You are moving like this because I1 is going upward and I2 moving downward. So, resultant upward is I1 minus I2. So, plus 2 into I1 minus I2 is equal to 0, or you just multiply both sides by 2, then you will get di1 upon dt plus 4 I1 minus 4 I2 is equal to 0. This is the equation 3 given. Now, similarly for loop 2, if you take loop 2, then if you make it loop 2, it will be 4 I2 right, plus 2 I2 minus I1, 2 I2 minus I1 right, minus 3I is equal to 0, because it is dependent voltage source is there 3I. So, in this case what will happen, it will basically 6 I2 minus 2 I1 minus 3I is equal to 0. This what I have written here, right, for loop 2. This is 6 I2 minus 2 I1 minus 3I is equal to 0. This is equation 4. Now, since I is equal to I1, right, therefore, you put here 6 I2 minus 2 I1 minus 3 I1 is equal to 0. That means, I2 is equal to 5 upon 6 I1. Now, from equation 3 and equation 5, right, in equation 3 actually you put this expression I2 is equal to 5 upon 6 I1. Then you will get di1 upon dt plus 2 by 3 I1 is equal to 0. So, this is equation 6. So, now, but we know that I1 is equal to I, therefore, di upon dt is equal to minus 2 upon 3 I, right, or di upon I is equal to minus 2/3 dt. Now, you integrate for on both sides. At t is equal to 0, current was I0, and at t is equal to at time t, current was IT. Di upon I is equal to minus 2 by 3 integration 0 to t dt, right, or IT is simply after integration you will get IT is equal to I0 e to the power minus 2t upon 3, that is for t greater than 0. This we have seen this kind of integration earlier. So, directly we are writing. Now, given that it was initially it was given that I0 is equal to 1 ampere. Therefore, IT is equal to e to the power minus 2t upon 3, because I0 initial value is 1 ampere given. So, put here I0 is equal to 1. So, it will be e to the power minus 2t upon 3. Now, voltage across the inductor is V is equal to L into di by dt. L is 0.5 Henry, right, and you take the derivative of the current IT dit upon dt. If you do so, it will be 0.5 into minus 2 upon 3 into e to the power minus 2t upon 3. Therefore, V is equal to minus 1/3 e to the power minus 2t upon 3 volt. Since the inductor and the 2 ohm resistor are in parallel, right. So, I mean V we have got, but look at the circuit, come to the circuit. So, this voltage across the inductor we have got, say this is voltage say V, this is voltage V, right. So, these two are in parallel, 2 ohm resistance and 0.5 that in Henry inductor, both are in parallel, right, and this voltage is say V. So, that means IY will be this same voltage across your 2 ohm resistor. So, it is V by this 2 ohm resistance, right. So, this is actually your current IY V upon 2, right, because this 2 ohm resistance is here. So, let me clear it. So, we will go back to that expression again. So, here it is IY at time t V by 2, the 2 is the 2 ohm resistance, right, through that is the current flowing through the 2 ohm resistance, that is IY t. So, it is V expression you substitute, V is equal to minus 1 upon 3. Actually, if you all the time I am not writing, but this expression actually it is all function of t, right. So, all the time I am not writing, but it is your what you call it is understandable, to you, right. So, let me clear it. So, that means in this case it will be minus 1 upon 6 e to the power minus 2 t upon 3 volt. So, now note that we select the inductor current, this is important, you should keep it in your mind. We select the inductor current as the response in order to take advantage of the idea that the inductor current cannot change instantaneously, right. Little bit more we will see that, right, at the time of opening or closing switch we will see that at t is equal to 0 minus or t is equal to 0 plus. So, we will see later. So, but this is that inductor current you are what to call as the response in order to take advantage of the idea that the inductor current cannot change instantaneously, right. So, this is one. Then another example is that the switch in the circuit shown in figure 16 I will show you has been closed for a long time before it is opened at t is equal to 0. Determine ILT, IT and VT, that is A, B, C, that A is ILT, B is IT and C, these three things you have to find out. And fourth, the D, the percentage of the total energy stored in the 0.2 Henry inductor that is dissipated in the 1 ohm resistor, right. So, this circuit I will show you, the switch in the circuit shown in has been closed for a long time before it is opened at t is equal to 0, right. So, this is the circuit actually initially it was closed for a long time, that means this circuit initially was closed for a long time and at t is equal to 0 it was opened, right. So, as the circuit initially was closed for a long time and at that time your how the inductor will behave, right. So, for DC we have seen the capacitor acts as an open circuit and for the inductor it will act as a short circuit, right. So, if you when this switch was closed for a long time, if we see the or what you call that equivalent circuit, then you see how is it, right. So, in this case what will happen that here I have not given that equivalent circuit. So, I have to make it for you. So, the switch has been closed for a long time and hence the voltage across the inductor must be 0 at t is equal to 0 minus, because it will act as a short circuit, right. And therefore, the initial current in the inductor is 2 ampere at t is equal to minus 0, that is IL 0 is equal, that means this one it was closed for a long time. So, inductor actually behaving as a short circuit. So, what will happen in that case, this 2 ampere current will flow through this inductor. So, IL 0 initially it will be 2 ampere, right, because it is acting as a short circuit, because switch was closed for a long time, after that it was opened. So, in that case as it is act short circuit, this will be ineffective, right, it is just take this short circuit path, because it acts like a short circuit assuming it is an ideal inductor, right. So, it is your your IL 0 is equal to 2 ampere, the initial current through of the inductor. Now, I am clearing it. So, now in this case, right. So, something is written for you, read it, same meaning. So, because an instantaneous change in the current cannot occur in an inductor. Now, as the switch is open, we compute Req. Now, when switch is open, when this switch is open, this is open, right. This switch is open means this is gone, this is not there in the circuit, but we know the initial current through the inductor IL 0 is equal to 2 ampere. So, in that case what will happen, if this is open, this 1 ohm and 4 ohm they are in your what you call in parallel, right. That means their equivalent resistance will be 1 into 4 by 1 plus 4 is equal to your 0.8 ohm, and with that this 2 ohm resistance is in series. Therefore, 0.2 plus 0.8, that the equivalent resistance is 1 ohm, right. And in that case time constant of the circuit will be tau is equal to L by R, right. So, it will be it is L 2 Henry and it is R. So, it will be 0.2 second. Now, another thing is this, look at the what you call the direction of the current flowing through this 4 ohm resistance, it is given, it is taken as I, right. So, first we have to find out that what is, and this direction of the current here IL is downwards, right. So, when you take the equivalent of this, let me go to that. let me go through that. Therefore, the tau is equal to, I told you R eq is equal to 1 ohm and tau is equal to 0.2 second. Therefore, the expression for the inductor current is, we know that ILT is equal to IL0 e to the power minus t upon tau, this we know. So, I0 is equal to IL0 is equal to 2 ampere, we have seen, and tau is equal to your L by R. So, it will be your 0.2 t minus t, tau is equal to 0.2 seconds. So, minus t by 0.2. So, it is e to the power minus 5 t ampere for t greater than 0. Now, the current I through 4 ohm resistor can easily be obtained by current division, that is ILT is equal to your IT is equal to minus ILT into 1 upon 1 plus 4. So, if you come here, if you come here, right. So, whenever we are your what you call this this 1 ohm and 4 ohm, they are in parallel, but this current I is flowing through this 4 ohm resistance, right. So, if you come like this, that your what you call that from the current division. So, this part of the circuit is not there, this part of the circuit is not there, right, and this is the your what you call that IL current, and this is the current your what you call I is coming your through this way, right. So, if you go for a your current division, right, then this I will be this I in, if you put in terms of t, it does not matter, IT is equal to, it will be minus, right, is current, it is 1 upon 1 plus 4 into your ILT, right. So, this minus is taken because of the your what you call, if you just try to find out your what you call that your just your direction, just for the way we have taken, right. So, so in that case, actually these two things, to your what you call, if you draw a circuit like this, that your 0.2 Henry, right, 0.2 Henry, and this equivalent resistance was 1 ohm, right, and this is your IL, this is your IL, that current is flowing IL like this, right. So, and this is this parallel equivalent is your 1 ohm, that circuit I have not done, but just showing you, and this is the 0.2 ohm Henry, and IL we have taken like this. So, this we have found out IL, right, but as the current division is there, so direction of this current your what you call is through your 4 ohm resistance, it is given this way, right. So, accordingly that your what you call this minus sign will be there. So, anyway, let me clear it. So, that is why your this IT is equal to minus IL into 1 upon 1 plus 4, that is minus 1 upon 5 ILT. So, that is IT is equal to minus 2 by 5, right, e to the power minus, this is a current division, simply the current flowing through this 4 and 1 ohm are in parallel. So, it will be current flowing to 4 ohm resistance will be your what you call that is 1 upon 1 plus 4 is equal to your that is 1 upon 5. So, minus 1 upon 5 ILT, and I told you that that your what you call that, because why it is minus, right. So, in that case IT is equal to basically minus 2 by 5 e to the power minus 5 by t, because ILT is equal to 2 e to the power minus 5 t is equal to minus 0.4 e to the power minus 5 t ampere for t greater than 0, right. So, now V is equal to your 4I, because 4 ohm resistance is there. So, across 4 ohm resistance the voltage is V is equal to 4I. So, 4 into minus 0.4 e to the power minus 5 t. So, V is equal to minus 1.6 e to the power minus 5 t volt for t greater than 0, right. Now, next is the power dissipated in the 1 ohm resistor is, that is P t is equal to V square by R. So, R is 1 ohm. So, that is 2.56 upon 1 e to the power minus your V square is your what you call, it is V square. So, 1.6 square 2.56 and it is square. So, e to the power minus 10 t. So, 2.56 e to the power minus 10 t watt, that is t greater than for t greater than 0. So, total energy dissipated in the 1 ohm resistor is that W t is equal to 0 to infinity 2.56 e to the power minus 10 t dt. If you integrate, you will get 0.256 joule, right. So, the initial energy stored in the 0.5 ohm 0.5 Henry inductor is half L0 square. So, half L is 0.2 Henry into IL0 initial value is 2 ampere. So, 2 square, that is 0.4 joule, right. Therefore, the percentage of energy dissipated in the 1 ohm resistor is, that is 0.256, that is your energy dissipated in the resistor 0.256, and initial energy stored was 0.4 joule. So, 0.256 by 0.4 into 100, that is 64%, right. So, with this, this is a typical your example for your circuit, just looking at the circuit, nothing to be worried. As the switch initially is closed, you find out what is the initial condition, then switch is opened, and accordingly you solve, right. And just looking at the plus sign or minus sign, please look into the your what you call the direction of the current, accordingly your, otherwise the sign your if you miss the minus sign or plus sign, if something goes wrong, then your numerical value may remain same, but the sign will create problem. So, little bit you should be careful, right. So, with your what you call, so all these things, I mean what are the, what are voltage, then energy stored in resistor 1 ohm, and percentage of the total energy stored, everything is mentioned in this problem. So, thank you very much, we will be back again.